first I'm going to talk about something called a multi-layer perceptrons. So we already talked about perceptron algorithm. So perceptron algorithm is for classification, right? Using linear combinations with the input and then apply a thresholding function such that you generate binary classification. And now we're going to talk about generalizations of the perceptron called multi-layer perceptrons. So next I'm going to talk about, this is a model here. So next I'm going to talk about how do you train this multi-layer perceptron, essentially how to learn the parameters of these multi-layer perceptrons using an algorithm called a backpropagation algorithm. And if we have time, we're going to talk about this more advanced topics here, more recent model, something called convolutional neural nets. So this is the models here underlying many of the successful models used in many different applications in computer vision, in natural language processing, many other domains of that. And I would say probably majority, many of them, I would say maybe in the 90% of the deep learning models are built based on the so-called convolutional neural nets. So I'm going to talk about that because this is such an important topic. So today, let's start talking about the multi-layer perceptron. So remember this perceptron algorithm. So perceptron algorithm is linear classifier. And what do we do here is that suppose your data is linearly separable. I'm going to find a separation plane or separating hyperplane to separate these two group data points here. And in two dimensions, the decision boundary is a straight line here. So for linearly non-separable data here, you have to make a mistake. You cannot completely separate the data sets there. So perceptron algorithm here, essentially you can think about it this. Suppose we have your input data have two features here, x1, x2 here, and we have parameter weight associated with x1, parameter mu2 associated with x2 here. And what do? We generate linear response here by using a linear combinations of the features here plus a bias term. And you got a response here. And then we can take a thresholding function on this response here. We generate either +1 or -1 here. So that will be your class decisions. And that's the perceptron classifier we talked about previous year. So the key idea here is this. One is the so-called linear combinations of the input here. And with the weight parameter, mu here, weight parameter is weighted summations of these guys here. And then the second part is this nonlinear functions here. And we apply, in the case of the perceptron, we apply a thresholding function here to generate predictions of 0 or 1, right? If you use a sine function, you generate -1, 1 here. If you just apply a thresholding function, you produce a result either 0 or 1 here. So that's the case of the perceptron algorithm. So for perceptron algorithm here, we say that, well, if your data is linearly separable and the perceptron is the algorithm you can use, and that's very convenient algorithm to do that. And however, what happens if your data is not linearly separable? What can you deal with that? So for instance, in this examples here, suppose you have one-dimensional data sets here, only one feature here. But in that case, you have data sets labeled with blue, some data labeled with red here. And if you just use one feature, using one thresholding function here, you cannot perfectly classify these data sets here. You always make mistakes. And how do you do that? Well, previously we say the way to address this problem here in order to generate a more complex decision boundary is to introduce nonlinear features. That's what we talk about. So what type of nonlinear features? Well, so far we talked about this sort of polynomial features here. So instead of x, I can introduce x squared here. If you do x squared, and maybe you can solve some of the problem with that, okay? So the question is this, well, for these examples here, and what type of polynomial features you can use to separate these two group data sets here, it's not clear. Certainly if you apply quadratic figure, it cannot solve, it doesn't solve the problem because you have this two red here and one blue here. So it doesn't really help in that case. The question is this, is there any other type of features we can choose? Of course, we say yes, you can choose any type of features as long as you have a particular functional form of that. So in fact, one of the most powerful type of features is this so-called step functions. The step function is very powerful features here. So why is that? Well, suppose I have a step function look like this one's here. There will be 0 and then go up to 1 here, 0, 1. But then those jump here happen at different locations of the features here. Suppose imagine you have x here. So now I have this feature here to simply to be a step function, but those step function apply at different locations of x here. So I can use these guys here as my features. And how this could be helpful? Well, because once you combine these type of features here, you can generate pretty complex functional forms. So for instance, say I'm going to do a linear combinations of these three features here, f1, f2, f3 here, and a times f1, b times f2, c times f3 plus bias terms here. And what I can do, let's say if I choose a equal to 1, b equal to minus 1, c equal to 1 here, and set d equal to 0, and you can choose this type of features here, and then go initially like f1, and then up to this point here, you subtract the f2, and now becomes drop to be 0 here, and then go up become f3. So now you have this type of functional form. So this type of functional form is not easy to generate using polynomial functions, but it's very easy to use this step function here. In fact, we just show here, using 3-step function here, you can easily generate this function form. So by doing that, you can see now, you can easily solve this classification problem if I use that 3-step functions. And you cannot do that using this polynomial functions here. You can see the power of the step functions, very useful. Well, so if this is the case, so let's think about this. And I can put all these perceptrons together, and then each one of them act as something like a step function. In the end, I combine them here. So this is more or less the ideas of so-called multi-layer perceptron models. So in the multi-layer perceptron models here, what do we have here is this. So each one of the nodes here is a perceptron. Is a perceptron here. You can think about perceptron produce a step function features. So you can see F1, F2, F3 here, and they are generated through a perceptron models here. So that perceptron take a linear combinations of the input here with these weight parameters here, produce a step function. That's the first perceptron. And I have a second perceptron produce another step function, a third step function here. And I put all these 3 perceptrons together, and I form a layer. I call those are 3 neurons in my layer here. And this will be something terminology, this I call the hidden layers of my models here. The hidden layer contains 3 perceptrons. These 3 perceptrons here are using the same x as the input, but combine them differently. So those weight parameters are different here. And then after you have generated the step function features, and then you can construct another perceptron here. This perceptron uses the linear combinations of these feature vectors here, the output of the perceptrons in the hidden layers, and then you weighted combine them, use another set of weighted parameters here, W1, W2, W3, and so on, doing that. So by doing that, you can produce output, something look like this ones here in the output layers of that. So that is the main idea behind multi-layer perceptron models. Essentially, is to apply this perception models repeatedly. You put perceptrons within the hidden layers, and then you construct an output layer here. Your output layers here using this perceptrons output as the input and produce a new output here. So it's kind of, you can think about this perceptrons here generate new sets of feature vectors and use that feature vector as my input to this output perceptron here. So this is so-called a multi-layer perceptron models here. The reason called a multi-layer here, you have an input layer, so terminology here is this. You have input layer here, and this is your hidden layer, you have output layer. So overall, you have 3 layers here. So the parameter associated with this model will be this. You have weight parameter from the input layer to the hidden layers here. So depending on how many hidden neurons you have here. And so in this case, you have three of them here. So for each one of them here, you have this weighted parameters here you need to determine. And then you have another set of weighted parameter that is from the hidden layer to the output layers of that. So overall, you have this amount of parameters of that. But the benefit of this type of model here is this. By combining these features here, you are able to generate more sophisticated features in the output layers of that. And hopefully, we can generate better predictions that way. Okay, So that is this kind of put all the perceptrons together. So what is multi-layer perception is essentially doing this. Instead of applying a hard thresholding function here, I'm going to make this function here more smooth, very smooth. Replace the thresholding function by a sigmoid function. So by doing that, I'm going to produce a feature here instead of a step function here, but kind of smoother versions of the step function. Similarly, the output here will be smoother versions of the step function here. You would generate something like here. The reason you get smoother versions of that because you replace the thresholding function by a so-called nonlinear activation function. For instance, you can choose to use sigmoid function as your nonlinear activation function. By doing that, you can generate smooth output of these feature vectors and also the output here. So that is the multi-layer perceptron models of that. So let's recap what we talked about here. It is. So in the multi-layer perceptron here, you have X here and send linear combination here and apply a nonlinear activation. And that will be treated as the output of this hidden neurons here. And then now you have the last layer, this outer layer here, receive input from the previous layers here, the output of the previous layer here, but they apply the similar mechanism, take linear combinations of them, and then apply this nonlinear activation functions of that, and that is the final prediction of your input here, and that's the multi-layer perceptron model. Okay, so let's do that again here. So in this case here, so let's think about the building blocks here. Typically, we think about this as a feed-forward models here. So this is input feature vectors here, and this is representing one neuron. So the terminology here, sometimes people call them as neuron or unit, so interchangeably. Sometimes we use both. You can think of this one neuron here. This is the input neurons here. This is neuron in the first hidden layer. And now you can take a second and third neurons of that. So this is the first layer. Now you combine them with the neurons in the output layers here. So now by doing that, you can generate a very complex feature space. So the idea is this. So this is so-called a multi-layer perceptron. In fact, you do not need to stop right here. You say, well, in this case here, this is my input. This is my prediction here. So, you do not need to stop here. You can say, I'm going to generate lots of features here and keep going like that. And then by doing that, you can say, I'm going to generate I'm going to put together another set of neurons in the second layers. And then I can use those output of the second layer as input to my final neurons here and make prediction this way. So by doing that, I now have a two hidden layers here. Overall, I have 1, 2, 3, 4 layers here. 2 hidden layer, 1 output, 1 input layer here. So now you can generalize from the previous multi-layer perceptron. And with only 1 hidden layer, I can have 2 hidden layers. And in fact, you do not need to stop here. You can keep going up with many hidden layers recursively. Now you have potentially have multiple layers of that. And that is the so-called deep neural nets. The deep because you can use multiple layers here, more than 1, more than 2, and that is called deep neural nets. So the benefit of this type of deep models here, deep architecture is this. The features you use become more and more sophisticated here. As we mentioned here, in the very beginning here, the features associated with the first hidden layer here is simply a step function. And then the features associated with these guys here is kind of combinations of step function here. So now in the outer layer, it's be combinations of these guys here. You can imagine that the complexity of the features will go up significantly. The things here become more and more complex this way. All right, so one thing here I want to talk about, I want to go back to the case of the multi-layer perceptron with only 1 hidden layer and then 1 output here. So that would be a simple case for, think about a regression or classification problem. This is the input here. I go up, first generate values in the hidden layer and then make predictions of that. So this is most of the old neural nets are built based on this so-called multi-layer perceptrons here with only 1 hidden layer. So even this type of models here, don't underestimate the power of this type of model. Even this type of models here, and people prove that this is actually very flexible enough that it can approximate any functional form. So which means Give me any arbitrary function goes from y to x here. I can use this architecture to model that arbitrary functional form. As long as you allow me to use arbitrary number of hidden neurons here. So that is the only complexity you allow me to do. So as long as you do that, and you can approximate any functional form. For these reasons, many people say that multi-layer perceptron is a universal approximator. So the reason it's called a universal functional approximator because it can approximate any functions of that. So it's very, so we demonstrate the power of this type of models. To see why this is the case, in fact, it's easy to see why this is the case. The reason is to think about it this. Well, suppose now you give me any arbitrary functional form. And let's think about it as one functional form here. Your input here contains only one x here. So the one-dimensional case. From x to y here, but the functional form is very arbitrary, very, any functions here. So now you can always approximate this function here with a piecewise constant function and approximate them, right? And the accuracy approximation will depend on how many piecewise constant you're going to put on this approximator here. And if you use an extremely large number of piecewise constant here, and that can see that you can approximate a function pretty well. If your function is kind of relatively smooth, you can think about it this way. Well, suppose now I use this type of piecewise constant function to approximate my function here, and I can show you that, and then I can use this, construct this neural net to generate exactly this type of piecewise constant function. And how do you do that? Well, the way you're doing this, you think about this. I'm going to replace this function here to be a thresholding function here. So now h1 here is simply in a step function here, and h2 will be step function here. So I'm going to choose this threshold of the step function here to be exactly located at this point here. So the first threshold here of h1 here will be at this point, exactly at this point here, at the boundary between v0 and v1. And the thresholding function for h2 will be at the boundary here, and so on. So you can choose the threshold for different function here this way. And the question, how do you choose the threshold function? Well, you choose threshold by choosing the weight here, or weight parameters here. By doing that, you can set the thresholding of each hidden neurons. Okay, so once you have this thresholding function here, now you can combine this thresholding function here with this by carefully choosing the weight parameter such that will go look something like this. Now, how do you do that? Well, so for h1, I'm going to choose the v0 to be the weight of h1 here, from h1 to y. I use the weight parameter to be exactly v0. And the weight parameter from h2 to y, I choose that to be the difference between v1 and v0. And by doing that, if I add them together here, I get v1 to be w1 plus w0 here. Now we exactly this values. So and so on. So you can see this idea here. So this will work perfectly well. So give me any function form here, I can approximate them with piecewise constant function. And as a result, I can use my kind of thresholding function here to approximate this piecewise constant function. We produce this piecewise constant function. In the end, it can approximate any functional form. So that just demonstrates the power of this model here. So so the power comes as the number of hidden units here. You can increase the number of hidden units here, even if you are using only one layer. So that multi-layer perceptron is also significantly powerful, have a higher capacity to approximate any function of that. So, but however, this is a theoretical concept. Nowadays, people prefer to extend the complexity model through the depths of the network here instead of the number of hidden units at each layers of that. So that's two ways to increase complexity. But increase complexity can be done, increase the number of hidden units at each layer, or by extending the number of layers. So today, people prefer to extend through the number of layers here for multiple reasons of that. So we can talk about later part of that. All right, so but now let's just stick with the simplest versions of the neural nets here. So the neural nets models here was proposed long time ago in the 60s and the 70s, and so it was originally proposed as a method to model biological neural networks. what neuroscientists discover is this: the neurons in the brain and typically receive lots of connections through so this actually the picture of the neurons here. It has this reach out here is called the dendrites here. Those dendrites receive input from all other neurons here. And then these neurons here internalize all this input here. And then in the end, will send out the output here through this kind of axon structure of that. So the axons here can be pretty long here. And then in the end, reach the terminals. And those dendrites here will interact with these dendrites from other neurons. And then through the transmissions of that. And then this is a neural structure. This is motivated people are saying this, I can model this biological neurons here with this simple model, perceptron models here. And with linear combinations of the input, and then I process them and then apply a nonlinear activation and send out the output of that. Of course, this is very simplistic views of these neurons. In reality, biological neurons is much more complex than the simple model we talk about here. And if you are interested enough, read any neurobiology book here. So all these interactions here are carried out through these ion channels, and the very ion channel, and also chemical channels, and through these neurotransmitters of that. So the interaction between them is very complex there. And this is the information is not simply done linearly, right? Because a lot of chemicals, signals are involved here. And then the information here was sent up through something called the action potential. So action potential itself is a binary here. But this binary is not the same as this threshold function we talked about here, because the information sent out is something called, is sent out through the neurons here is encoded through the frequency of that action potential. So it's slightly more, very complicated situations. But in any case, the model we use here is, you think was originally what was motivated by this kind of biological neurons is a simplification, but it turns out it works okay. So, so in terms of activation functions here, there are multiple choices of this nonlinear activation functions. So I just here list a few of the most common choices. So the ones I talked about here is the logistic units here. And logistic is the same as logistic function we talked about previously for the binary classification case. This is the values between 0 and 1, and there is a squeeze between 0 and 1. If your z is very negative, that goes to 0, and if it's very positive, it goes to 1. If it's 0, it's 1/2 here. So that's the sigmoid function. So one nice thing about the sigmoid function is that its derivative is very easy to calculate. It's simply equal to sigma times 1 minus sigma here. And then this logistic unit here, the output is a range between 0 and 1. So some people don't like that. They want to have something to be centered around 0. So you want to produce something between -1 and 1. How to do that? And this is the generalization of the logistic function called hyperbolic tangent functions here. So in this functions here, looks pretty similar to logistic function. The only difference here is the output here is a range between -1 and 1 here, and centered at 0. So the logistic unit here, if your input is 0 here, it'll give you output of 1/2. So this is, however, in the hyperbolic tangent case, if your input is 0, the output is 0 as well. So that is somewhat people like this type of models here, called hyperbolic tangent. And then of course there are a few other choices here. And this turns out the first choice is so-called a ReLU activation function, and it stands for rectified linear function. So this function is very interesting. It's a piecewise linear functions here. And this function is saying this: if it's negative, give output of 0. If it's positive, that would be the linear functions of the x here, the same as the x here. So it goes from 0 and then the x here. And that's called a ReLU activation function. So in the functional form, it simply take the maximization between these two numbers here, either 0 or z. So which means if z is negative, so that value is always 0. If z is positive, that's simply equal to z values here. That's the rectified linear. Of course, you can use linear activation function. In fact, this is a very common choice. This applies to the neurons in the output layer, in the case of the regression problem. Because for many cases, the regression problem is that the values are unbounded, not bounded. So you cannot apply this type of function because they will bound the values of the output here. So in that case, a much better way is to apply a non-bounded activation function. The simplest choice is simply a linear function of that. So these are various different types of the activation functions. And there are, so these are the first few, and linear was proposed a long time ago. ReLU was also proposed quite a bit some time ago, but it becomes very popular recently. And kind of surprisingly enough, nowadays this becomes the most popular choice for the deep learning models of that. So people like this type of models use this as activation function for various reasons. And if we have time, we're going to talk about that. So why people choose ReLU instead of logistic. So in the old days, almost everyone chose either logistic or hyperbolic tangent. But this is more recent way choices. All right, so let's talk about again. So in terms of implementation, it's quite easy here. Typically we speak the types of network we talked about so far is called a feed-forward network here. Essentially, you calculate this, you can make predictions through layer by layer fashions of that. You start with the X, and then you calculate the activations of the hidden units here. And how do you do that? We take the W here times the X here in dot product between them and take a bias, and then you apply nonlinear activation functions of that. Suppose your nonlinear activation is the sigmoid here, you apply nonlinear activation. And once you have this activation here, and then you apply similar ideas, now with different sets of weights. The W applies to H and so on. So this is so-called a forward pass. By doing the forward pass, you calculate the activity of each individual neurons. What I mean activity is just the output of each individual neurons here. In the end, you can generate predictions. So this is called a feed-forward pass. All right, so now you can think about it for specific types of problems here. And now suppose you have regression problem here. You have two neurons here. You might want to predict two values of that. And that would be for regression of two labels here. And you can also think about it, you can solve a classification problem here. And then suppose for binary classification, you should predict the binary values of 1 here. For multi-class classification, it's very common to use multiple output neurons here, just in the case of the softmax predictions. We're going to produce the probability vectors for C different classes of that. So you're going to have C output in the output neurons of that. And you can train those models here, and then apply a loss function, and then using gradient descent to learn the parameters of the models here. And that's using the similar idea what we learned the previous year. So let's revisit what we talked about here so far. So the parameter of the models here is this. Are those the weight parameters here, the connection between the neurons, there's a weight here, and then the bias associated with each individual neurons of that. And then how do we train them? Well, the train them is saying this, well, what are we going to do? Give me a pair of examples here, X and Y. Given X, I make predictions. And then I'm going to compare my prediction, Y hat, this is the output from the neural nets, and compare this predicted values Y to the ground truth, the target value Y here. And that will be the loss function you can formulate. For instance, if you are using a regression problem here, that will be mean squared error loss you can calculate here. And then the question is this, for optimizations here, I'm going to minimize this error here with respect to the parameters of the models here. And then I'm going to use optimization algorithm to solve the learning problem. So, so in general, optimization, we're going to use the similar optimization methodology we talked about previously, namely the gradient descent methodology. We can either use batch gradient descent or modern version, we use something called stochastic gradient descent. So the difference between batch gradient descent and stochastic gradient descent is the following. So in the batch gradient descent, you calculate your gradient by using all training examples. And suppose you have 100 training examples here, your gradient calculation is going to be based on the gradient of all 100 samples. So typically, is the mean gradient over each pairs of examples here. And that, if you use that gradient to update your parameters, that's called a batch gradient descent. So similarly, you can apply a slightly different versions of the gradient descent methodology, something called a stochastic gradient descent method. So in this method here, we talked about previously, in the perceptron learning algorithm, we talk about this online learning algorithm. So in that case, you update your parameter based on one sample only. So that's online gradient descent. And you can do something between online gradient descent and batch gradient descent is something called a mini batch gradient descent algorithm. So in that case, your gradient is calculated based on random subset of your entire training samples. And suppose you have 100 samples, and let's say I only randomly sample 10 samples and use the gradient based on these 10 samples to update my parameters. And that version of the gradient descent is going to be called a stochastic gradient descent algorithm. So of course, nowadays, everyone is using the stochastic gradient descent algorithm for multiple reasons. And if we have time, we can talk about that. But now you have to think about it, get used to this idea that calculate implement the algorithm based on the so-called SGG type algorithm. But by any case, in order to implement this algorithm here, we need to know how to calculate the gradient of the error with respect to the parameters of the model. The way we're doing this one here is going to apply an algorithm, something called a back propagation algorithm. So the back propagation algorithm, in fact, is not new. It's not something very magic or very new. It's simply the chain rule from your calculus. So by this, what I mean here is this. Suppose you have this functional form of j here. Suppose you have function j here. J is the functions of the f, and then f is the functions of another function here, g and h here. So now, suppose I want to calculate gradient of this j function here, and suppose that's a loss function. I want to calculate the function j with respect to g. How do I do that? Well, the way you do it is this. You calculate gradient with respect to f first, okay? And then you calculate gradient with respect to g by doing this, by applying the chain rule. Is this gradient with respect to g is going to be gradient of j with respect to f, and then gradient of f with respect to g here, right? You calculate this first, and then calculate this one to derive these guys here. And similarly, in order to calculate gradient of h here, you calculate gradient with respect to f, and then calculate gradient of f with respect to h here. And using this type of chain rule, and you can calculate this gradient with respect to h here. So in fact, that's it. So the gradient, so-called back propagation algorithm, is nothing but just apply the chain rule repeatedly. So let's take this as examples here. Suppose I only have one simple model here, one multilayer perceptron here. I have a loss function. The output is this. The loss function is the square loss functions here. I have this output layers here. You can apply a nonlinear some activation function here. And that would be the linear combinations, the input from the hidden layer with this weighted parameter W here. So that is the prediction here. And for the hidden layers here is this nonlinear the linear combinations, the input here, apply nonlinear activation function. Okay, suppose now I want to calculate the gradient of this loss function here with respect to these parameters here. W2 is represent the parameter from this hidden layer to the output layer. W1 represents the parameter from the input layer to the hidden layer here. And how do I do that? Well, we're going to apply gradient respect WK here. Is relatively easy. You calculate gradient J respect to Y hat here, and then calculate gradient of Y hat respect to W here. And that's what you hear. This is gradient of J respect to Y hat. This is a quadratic function. That's this form here. And then calculate gradient of the Y respect to H, and that in this form here. And that by doing that, you calculate, you know that what's the gradient respect to the W2 parameters here.